Okay, welcome back, everybody. At the end of class yesterday, I had kind of ended with this fact that I said that we're going to use to find roots of a complex number. So I noted that if we have two complex numbers, they're already in exponential form here. These two are equal if and only if the r's match up, right? So these radii match up, and the thetas differ by a multiple of 2 pi, right? An integer multiple of 2 pi. Okay, and so we're going to use this together with the fact that we know how to easily exponentiate things in exponential form to find the nth roots of complex numbers. So what does it mean if I'm finding nth roots of a complex number? So if I wanted to find the nth roots of some complex number, say z naught. So we'll say z naught is r naught e to the I theta naught. Okay. So if I wanted to find nth roots of some z naught, what does this mean? It means, i.e., I want to solve. So I want to solve the equation z to the n is equal to z naught for some z naught, right, that I've listed above using this notation. Okay. So I'm looking for solutions to this. Okay. Written another way, of course, I could say that I'm searching for z that are the nth roots, right, of z naught. So I'm searching for z that are nth roots of z naught. So I already spilled the beans a little bit yesterday, saying that this is going to be something that works differently for the reals, right? For the reals, if I talk about the fourth roots of 1, for instance, it's a pretty easy thing to talk about. But for the complex numbers, it's a little bit different. But it's nicer in a lot of ways because the answer is always the same. When you ask how many nth roots does a given non-zero complex number has, the answer is n. Okay, and we'll see exactly how that works. So this is what this is actually what I'm looking for here, right? So I'm looking for solutions to this thing. Okay, and so how do I go about doing this? Well, actually, right, if I write z in its exponential form, so r e to the I theta, okay, so I've already mentioned that I want to use the fact that I know how to exponentiate, right, and this fact that two complex numbers are equal if and only if the r's, these radii, match up and their arguments differ by an integer multiple of 2 pi. Okay, and so using those facts together, what this means is that if I look at this equation, z to the n is equal to z naught, replacing both of these things. This occurs if and only if we have, so z to the n, this becomes r to the n e to the I theta times n, so I'll put the n right here, and that is equal to z naught, which is r naught e to the I theta naught. Okay, so then what does this mean? I want to combine this with this boxed fact here, right, that I wrote yesterday. Well, there. Now I'm on the screen. So the two complex numbers are equal, as I have here, if and only if these r's match up and their thetas differ by integer multiple of 2 pi. Okay. So what this means for this expression is, of course, that r to the n must equal r naught, and n times theta must be theta, as I've or theta naught, as I've written here, plus some integer multiple of 2 pi. Right. So k is 0, 1, 2, and so on. Okay. well, actually, I mean, this is allowed to be an integer multiple, so these can be plus minus 1, plus minus 2, and so on, right? Okay. Well, if this is the case, this actually kind of nails down what it is that's going on here entirely. And so, first of all, from the first expression here, I see that r is the nth root of r naught. R naught's a positive real number, right? So this is not an issue. Nth root of positive real number, that always exists, so that's fine. And if I solve for theta here, from this expression, theta is just theta naught plus 2k pi over n. Right, and k is some integer. Okay, and so we've actually found the generic form that any nth root of some complex number has to take, right? And so, just writing this out, thus the complex numbers given by z is the nth root of r naught times e, I'll write it like this so that it's more clear, times e to the I times theta naught over n plus 2 pi k over n are nth roots of z naught. So are nth roots of z naught, which is r naught e to the I theta naught. Okay, i.e. z to the n for each of these z is equal to z naught. Okay, so this does it, right? Where k is some integer. In fact, the fact that we can choose k to be whatever integer we like here, and this fact still remains, that these are all nth roots of this complex number we started with. This tells you that, you know, this expression is giving me infinitely many roots here, right? Now, if you think for a second what's going on here, you see that we'll eventually, right, for, say, we'll think of just larger and larger k, you're going to start getting repetitions here, right? So how many of these are distinct? So how many of these are distinct? Right? So how many of them are actually different from one another, right, before I start getting repetitions? The answer to that question is n. Okay, n. And so there are n nth roots to a given complex number. Okay, you're going to see that we can also apply this to complex numbers that are real, right, that have imaginary part 0. So for instance, we are going to be able to apply this, for instance, to talk about the fourth roots of 1. Okay, so the fourth roots of 1, and we're going to have 4 of those. We're going to have 4 distinct fourth roots of 1, for instance. Okay. All right. And so, where do I get the distinct ones from, right? So, second question. Which are the distinct roots? How do I obtain those from this expression? Well, the distinct roots are just the ones where k is going from 0 up to n minus 1. Okay, so if I choose k 0, 1, 2, 3, and so on, all the way up to n minus 1. Okay, those give me the distinct roots. Why though? Why is this the list? Could I make any other list of choices of k to get the n distinct roots? The answer is yes, right? I could start literally at n and go to n plus 1, n plus 2, n plus 3, and so on, all the way to n plus n minus 1. right? And also get the same list of roots. But notice what happens when you choose k equals n. When k is equal to n, in this expression, you would have 2 pi n over n, so the n's cancel, and you would have this theta naught over n plus 2 pi. So whatever this angular value is, you would be adding 2 pi here in the argument, which of course does nothing, right? Since we know that this exponential form, right, by Euler's formula, depends on cosine and sine. Cosine and sine are 2 pi periodic, so adding in 2 pi in the argument does nothing there. And so actually that's the same as starting at k equals 0. Okay. So I encourage you to think about that. You're going to have plenty of examples of working through these things. So there's some in the homework as well. There's a few examples of me asking you to compute roots of complex numbers in the homework. Okay, so next then, what is a nice, easy way to see where these things are in the complex plane? Okay, first of all, we're going to label, so we label the nth roots of, say, z naught as c sub 1, c sub 2, c sub 3, all the way to c sub n. And so we label them in the following way. So we would say c sub k is defined to be the nth root of r naught times e to the I times theta naught over n plus 2 pi k over n. All right, and this is for k going from, let's if I want to make this so that I don't have to shift any indices, let's do this slightly differently. Let's label them from c sub 0 to c sub n minus 1, so that k can go from 0 to n minus 1. That will save us some headaches. Okay. So there's n of these, right? So there's n of these inserts. This is convenient for not having to see. We just have generic z. So this is going to, when I write this, I'm going to be able to nicely list out these things. What do these things look like? It turns out these have a very nice geometric description. So these c sub k are arranged along a circle of radius, well, let's look for a second, right? We have these c sub k in their exponential form here, so then we can immediately see what circle they lie on. Here's the radius, it's the thing multiplying the exponential term. So it's the nth root of r naught, right? So they lie along a circle of radius nth root of r naught. Okay. And they are equally spaced. Okay. So they are equidistant along this circle. What would it mean to be equally spaced for these nth roots? It means the angles between them, i.e. angles between successive roots are 2 pi over n. Okay, and so what does this look like? Well, here's I should say the circle of radius nth root of r naught is centered at the origin. So here's my circle in question. The nth roots are equally spaced. Of course, where they are located depends on what n is. I've already messed up here. They're equally spaced here so that between each of these things is an angle of 2 pi over n. So the next angle is 2 pi over n as well. Next angle is 2 pi over n, and so on. All right, so maybe if here is C0, here's C1, here's C2, and so on, all the way around, equally spaced. Okay, in this way. All right. Okay. And so, there is a kind of more convenient or snazzier way of thinking about these nth roots, which is if I use the expression z0 to the 1 over n for this, if I say that this is the set of nth roots of z0. So this has n members, right? There's n elements of this set. Okay, and so in this case, it makes sense to actually talk about a principal root. Okay, and so the principal root, so the principal root of z0 is one where theta 0 is chosen from the argument of z0, right, such that it is strictly between minus pi and pi. Right. Now, what is the benefit in choosing a principal or talking about a principal root? Well, it's just so that we can actually have some like specified starting point, because otherwise it can be hard to keep track of what these things do, because they behave actually similarly. And we'll see that it doesn't actually matter that much. You could actually do the analysis where, like the things that I'm about to write out, I'm going to use this principal root C0. So the principal root C0 I'm going to use in the following algebra, but it turns out I could have actually used any of these roots. It's just nice to have one that, you know, is easy to nail down and to specify. Okay, this is your point of reference here. Okay, and so going back here, this is my expression for these roots, C sub k. I'm going to write this in a slightly different way. Namely, I'm going to break this up using the exponential rules here. I'm going to split this thing up into two exponential terms, and you'll see why we're going to do that a little bit later. So C sub k is the nth root of r0 times, just to remind you, times e to the I times theta naught over n times e to the 2 pi k, or I times 2 pi k over n. All right, so this is just another way of writing this, where k goes from 0 to n minus 1. Okay, and so I'm going to write this in a slightly nicer way here. So the way that I'm going to write this is define omega sub n to be e to the 2 pi over n, or sorry, e to the I 2 pi over n. Okay. Okay. You'll see later why I've chosen this. Then, if I raise this to the kth power, so omega sub n raised to the k, is using our exponential rule here for exponentiating an expression like this. This is e to the I 2 pi k over n. But that's exactly that term. Okay. And so what this means is that I can rewrite this c sub k in the following way. I can note that, first of all, the principal root, if I've actually chosen theta naught from the argument of z naught such that this theta naught is between minus pi and pi. If I've done that already, and I'll just assume that I've always done that, because of course I can always choose such a value from this thing, so I'm just going to always pick the nice one here. So let's say that I've done that already. So then this c naught is the principal root, and that actually shows up here. Right there it is, right there. It's this piece. And so c sub k is c naught, right, which is this piece, times omega sub n to the k, for k equals 0, 1, all the way up to n minus 1. Now this is a really convenient way of characterizing these roots. Okay, here's the part where I said that my choice of principal root c naught, I could have actually done a similar thing here where instead of c naught I could have actually picked whatever root. So I didn't actually have to choose this theta naught in this way. I could have started with any theta naught I wanted to and used any other non-zero root. It didn't have to be the principal root. I could still do this. So all that is doing is, if you imagine the roots as being, you know, arranged over here. So here's c sub n minus 1, right? Here's the last one. If you imagine these roots being arranged all along the circle, starting at not the principal root would just be starting somewhere else on the circle and going around. But you're still getting all of them in, you know, in that order. Okay. All right. And so, if you worry about, you know, remembering on the fly this formula for computing nth roots in this way, an easy way is to basically do what we have kind of done to remember all these algebraic properties involving exponential form, and which is why I wanted to justify it using power series. Was to say that it actually is, right, the exponential function. So you can use all those exponential rules all you want to. So actually, all you have to do is just think, okay, I'm going to actually treat this as z naught to the 1 over n. And I'm going to use all of the rules of exponentiation that I normally do. So if z naught is 1 to the n, this is r naught e to the I theta naught. Of course, if we're writing this in the absolutely most general form here, this would be I times theta naught plus 2 pi k, right? And that would be raised to the 1 over n. But hey, I mean, that's r naught to the 1 over n, e to the I times 1 over n times theta naught plus 2 pi k. And that's exactly what we end up with. We end up with, you know, this is nth root of r naught. This is make this nicer, the exponential function of theta naught over n plus 2 pi k over n. Okay, so this is a easy way of just remembering how this is done. Okay, all right. So that's all of the general way of actually doing this. How do I actually find these roots? So I think I even gave you this one for the homework. So here's, you know, this is basically how these homework problems of finding the roots go. So let us find all values of minus 8i to the 1/3, i.e., we are finding all roots, or all third roots. I should say all 3 third roots of minus 8i, or all solutions to the equation z cubed is equal to minus 8i. Okay, so I know I'm beating it over your head now that you know, these are all the same thing, and I'm going to stop that. This will be the last time I I do this. But when I write an expression like this, right? Remember, we're writing this as a set, right? So you shouldn't. Your real analysis bias shouldn't come in here. You should think about this as this is not a single value. This is a set. So minus 8i to the 1/3 is the set of all solutions to the equation z cubed is equal to minus 8i, which is all the third roots of minus 8i. Okay, and so let us write this first in exponential form here. So what is minus 8i? So minus 8i needs to be written in exponential form. What is that in exponential form? So minus 8i is, well, what is r here? Well, r would be square root of 0 squared plus minus 8 squared. So it's square root of 64, so it's just 8. So r is 8 here. Okay. And what is going to be theta? Well, let's think where minus 8i is located. Minus 8i is here, right? Minus 8i is on the negative y-axis. And so what is my principal argument here? I'm not going to go all the way around here. I'm going to go here. This is minus pi over 2. So that's my principal argument here. So rewriting this, this is 8 times e to the I times minus pi over 2. Now you're tempted to just stop there, right? You're tempted to just stop there. But of course, if you're being as general as possible here, we should include the fact that, well, actually, we could have this exact same expression for any integer multiple of pi here. Okay. All right. And so now that I have written minus 8i in its exponential form, most generally even, right, including all this, and here's my principal argument right there. Well, how do I compute these roots, c sub k? So according to my formulation, there should be 3 of these, right? There should be c naught, c1, and c2. Okay, so what is c sub k according to my formula? Let's go back here. All right, here's my, there it is. So c sub k in this case is the third root of 8, right? Because that's r naught, right? So if I'm viewing this as r naught here times e to the I theta naught plus 2 pi k, or 2k pi. Okay, then this is cube root of 8 times e to the I times, I have minus pi over 2 over 3 plus 2k pi over 3. Okay, and of course k is either 0, 1, or 2. Okay, so let's write this in a slightly nicer way. So cubed root of 8, that's just 2. So this is 2 times e to the I times minus pi over 6 plus 2k pi over 3. Okay. All right. So what do these look like? All right, what do these look like? Well, let's actually draw some of them. Okay, so these are going to be arranged around a circle of radius 2, centered at the origin. Okay, so let's draw my circle of radius 2. It's really bad circle. Okay, so here's my circle of radius 2. Alright, so then let's actually write out what these c's are. So c naught the principal root is going to be 2 times e to the minus I times pi over 6. And c sub 1 is going to be 2 times e to the, so c sub 1, I'm choosing k equals 1 here, so when k equals 1, this is minus pi over 6 plus 2 pi over 3. And so that is e to the I pi over 2. So this is e to the I pi over 2. Okay. And c sub 2 is 2 e to the, maybe I'll write this out, right, if there's confusion here, right? So I'll write out what I did there. So this is 2e to the I times minus pi over 6 plus 2 pi over 3. Okay, which is e to the pi e to the I pi over 2. C sub 2 is 2 times e to the I times, so here I have minus pi over 6. If k is equal to 2, this is 4 pi over 3, right, which is 8 pi over 6. So that's this is going to be 7 pi over 6 here. And so this is 7 pi over 6. So there's my 3 roots. Okay. Now, of course, if I stop for a second and I'm like, okay, well, where are these on the circle, right? So drawing them on the circle is easy enough. So here, I'm on the circle of radius 2, e to the minus I pi over 6, remembering Euler's formula, right, that e to the I theta is cosine theta plus I sine theta. Then e to the minus I pi over 6 is going minus pi over 6, right, clockwise from the positive x-axis, and there it is, right? There's C naught. Okay, so that's minus pi over 6 from the positive x-axis. Of course, I could actually find the coordinates here if I wanted to. That's something I can do. But I can just tell, because these things are equidistant, like where the next ones are going to be. And also, this one is actually easier even to see, because like if I look at C1, right, this is 2 e to the I pi over 2 here. By Euler's formula, this is 2 times cosine pi over 2 plus I sine pi over 2. Right? And so this is 2 times cosine pi over 2 is 0 plus sine pi over 2 is 1. So this is 2 plus, or 2 times 0 plus I. This is 2I. Right? So this is here. There it is. Right? Okay. So there's C1. And then C2, of course, is going to be 7 pi over 6, which is, there's 6 pi over 6. 7 pi over 6 is here. But I could have determined it anyway because it has to be equidistant. These actually form an equilateral triangle here, right? If you connected these like this is an equilateral triangle. Okay, because they are equally spaced around that circle of radius 2. Okay. Again, I took a shortcut here by just drawing the picture, but if I was actually asked to find the, say, real and imaginary parts of this one, how would I do that? Well, I would just say, well, C naught is 2, e to the minus I pi over 6, which is 2 times cosine of minus pi over 6 plus I sine of minus pi over 6. And you can compute those, right? So I believe in the homework I asked for both the real and imaginary parts of these, so that is exactly what you would do to find them. Okay. All right, and I'm going to stress one thing here, that note I can write these in a particular way here. So I'm going to go back and I'm going to write, so C naught is 2e to the minus I pi over 6. Okay, C sub 1 can be written as, going back to my description here, I'll put this at the top. All right, this can be written as 2 times e to the minus I pi over 6 times e to the I 2k pi over 3. Remember what I wrote here when I came up with this alternate notation. Let me bring it back. I had this alternate notation here. So omega sub n was e to the I 2 pi n, which meant that omega sub n to the k is e to the I 2 pi k over n. So this is actually, notice this is just C naught. So this is C naught times omega sub 3 to the k, right? In that case, sorry, this isn't k here. This k is actually equal to 1, so this is omega sub 3 to the 1 here, right? So this k is actually a 1. Okay. So that's 2 times 1 pi over 3. And C sub 2 is 2e to the minus I pi over 6 times e to the I times 2 times 2 pi over 3, which is, again, C naught is exactly the same, the principal root, times omega sub 3 squared. And so if I look at this list of roots here, this is my principal root times omega sub 3, and my principal root times omega sub 3 squared. Those are my 3 distinct roots. This is why it's nice to think in terms of the principal root here, because actually from the principal root and from these omega sub n's, I can generate my whole set of roots. Okay, so those omega sub n's are particularly nice. Okay, they're particularly nice. What are they and what are they doing? So that's what we will discuss right now. So I want to figure out what it is these omega sub n's are doing. Okay, so to do that, I am going to consider the following problem. Okay, I have told you that every complex number has n nth roots. Okay, so if I didn't lie to you, then this applies even for complex numbers that happen to be real, right? That happen to have imaginary part 0. So let us find all nth roots of 1. So I want to find all nth roots of 1. Okay. Well, how would I do that here? So, right, so my z naught is equal to 1, and I'm looking for solutions to the equation z to the n is equal to 1. Okay, well, as with all of these, I begin by putting 1 into exponential form. Well, 1 is, of course, the complex number 1 plus 0i. So r is 1, right? Square root of 1 squared plus 0 squared, that's 1. And thinking about where this is, of course, in the complex plane, there it is, there's 1. Okay, and so what is its most general exponential form? Well, it's 1 times e to the I times 0 is its principal argument, right? Because it actually lies on the positive x-axis, plus 2k pi. All right, where k is some integer. This is the most general form for this thing. So then if I'm computing the nth roots of 1, how would I do that? Well, this would be the nth root of 1 times e to the I times 0 over n plus 2k pi over n, where k runs from 0 up to n minus 1. Okay. But if I simplify this, this is just e to the I times 2k pi over n. But this is omega sub n to the k, right, using that previous notation, where omega sub n is equal to e to the I times 2 pi over n. And so what are the roots of unity, or the roots of 1 here? So then the nth roots of 1 are the set, well, there's me taking the 0, right? This is the, when k is equal to 0 here, right? Anything raised to the 0 power is taken to be 1, so that's just 1. And then I would have k taken to be 1 here. So this is just e to the I 2 pi over n, which is just omega sub n. And then if I take k to be 2 here, this would be omega sub n squared, and then omega sub n cubed, and so on, all the way up to omega sub n to the n minus 1. Right? So those are my nth roots of 1, where omega sub n is this principal root, right? Where well, it's actually the root where k is equal to 1 here. So it's me taking k equal to 1 here. So it's actually not the principal root. Okay. What these are, so these are called the roots of unity. So they're nth roots of 1. 1 is here taken to be unity, right? 1 is the unit, so roots of unity are what these are referred to as. And you see exactly why these are important. Let's go back to my previous example, right? So in my previous example, I found that my 3 third roots of minus 8i, right? So this is what I was computing. Okay, and I found that I could actually characterize those in terms of the principal root, c naught, and these roots of unity. So in fact, even 1 is showing up here, right? So c naught times 1 is the first, c naught times omega sub 3 is the next, and c naught times omega sub 3 squared is the next. And so these roots of unity, these nth roots of unity, show up in me computing any of these roots, okay, naturally. And that's why we made a big deal of splitting off that omega sub n term in our formula for this. Okay. So if you want to see some nice examples of nth roots of unity, so here's pictures of nth roots of unity. So nth roots of unity for, we'll do the case n is equal to, say, 3, 4, and 6. Okay, so if n is equal to 3, we'll do that here. We'll do n is equal to 4 in the middle. We'll do n is equal to 6 over here. So what does this look like? So, of course, they're around unit circle, right? So here's unit circle in each of these cases. Okay, and so so 1 is there, These have to be equally spaced. So where is omega sub 3? You could actually find this if you like. This is omega sub 3 would be here, and omega sub 3 squared would be there. And these would form an equilateral triangle. It doesn't look equilateral because my circle is bad, but forgive me, please. Right here. You believe my diagram, right? You would never think that those angles are not all congruent. Okay. So all these circles are unit circle. So for n equals 4, of course, here's the first one. Once you know that and once you know they're equally spaced, you know where the others have to be. Right? And of course, you could draw a regular polygon connecting those things. I'm not going to because it wouldn't look anywhere close to a square, and I don't want to embarrass myself further. But here's one. Here would be omega sub 4. Here's omega sub 4 squared, and here's omega sub 4 cubed. All right. And then lastly, the sixth roots of unity. So here's 1, and then I would have omega sub 6 would be like here. And here's omega sub 6 squared. And here's omega sub 6 cubed. And here's omega sub 6 to the 4th. And here's omega sub 6 to the 5th. Equally spaced along unit circle. All right. Okay. So, one more example maybe before moving on to discussing regions, and then finally talking about functions of complex variables. So a quick computation of, say, the roots of, say, the square roots of square root of 3 plus I. Right. So if I wanted to compute this, I first put it into exponential form. So root 3 plus I. This is, so the modulus of this is 2. So this is 2 times e to the I times, what is its argument? Well, this would be, this is cosine, this is sine, so this is pi over, this is pi over 6. So this is pi over 6 plus 2k pi. This is the most general form of this thing. So then my square roots for k equals 0 and 1 going to be square root of 2 times e to the I times, so this is pi over 6 over 2, so that's pi over 12, plus k pi, because I'm dividing by 2 here. And of course, k is either 0 or 1. Okay. And so then, c sub 0 by Euler's formula is square root of 2 times e to the I times pi over 12. So that is square root of 2 times cosine of pi over 12 plus I sine of pi over 12. Okay. And then c sub 1, of course, is if I'm finding square roots here, right? Once I find c naught, then c sub 1 is easy to find because it's exactly on the opposite side of that circle, right? So note that c sub 1 is opposite c naught on the circle. Modulus of z is root 2. Okay. And so you can actually find exactly what the real and imaginary parts are if you use some power reduction identities here for cosine and sine to get at those angles. So I will leave that to you. The textbook does this at the end of section 10 in chapter 1. Okay, so one more discussion that has to take place before we can actually start doing analysis of functions is one that concerns the topology of regions in the complex plane. So regions in the complex plane and their topological properties. Okay, so what do I want to focus on here? Well, first of all, kind of the basic region that we're going to discuss is called an epsilon neighborhood. So this is the set of all z such that the modulus of z minus z naught is strictly less than epsilon. Okay, so this is called an epsilon neighborhood or just a neighborhood. So this is called an epsilon neighborhood. Or just a neighborhood. Or abbreviated as neighborhood like this. Okay, so I don't have to write that word all the way out. Okay. You'll notice that this is similar to the notion of an epsilon neighborhood in real analysis, but in real analysis, when you're talking about a function of a single real variable, this is, an interval on the real line. Here, just note, like, what does this region look like? Well, this describes the interior of a disk, right, centered at z naught. So here's z naught. The collection of all complex numbers z that satisfy this inequality then is, I've drawn this before. I drew this a couple days ago. So here we go. Epsilon is my radius. It is dashed because it doesn't include this circle, right? The circle of radius epsilon centered at z naught would be this, right? Okay, but it doesn't include that. Okay, and that's why it's dashed. All right. So it's all the points that lie inside the circle but not on the circle of radius epsilon centered at z naught. Okay. Sometimes we want to talk about what's called the deleted neighborhood. So what is a deleted neighborhood? Let me separate this out so that you don't think this is the deleted neighborhood. So deleted neighborhood here is a punctured disk. A punctured open disk. I'm throwing that word in because it's kind of unavoidable to be right here, but we'll talk about all those words here in a second. So this is similar to the epsilon neighborhood, but it's also bounded below strictly by 0. What does this do? Well, I would have so here's my z naught, but instead of actually being a point filled in, it would be a hole. So here's z naught, and here is the epsilon neighborhood around z naught. But the point z naught itself isn't included. So it's exactly the same as this epsilon neighborhood, except I've taken the middle point out. It itself is not included. It won't become clear why this is useful until a little bit later, but this is definitely going to be useful. It's something we're going to have to talk about. So it's a way of talking about an epsilon neighborhood without including the point that it's centered at. Okay. All right. So that's a useful notion. Now I want to talk about some of these, when I say topological properties, in case you've never heard that word before, or in case you don't know what exactly a topology or what a topological property is. This concerns properties of openness and closedness in some set. Okay, and so we're not going to do this in like perfect topological generality because there's no purpose for it, for what we're going to use it for. But we still have to talk about a lot of these terms because we're going to be tossing them around, and it's very important that you know what these things mean, because if you don't, then a lot of the if you take a statement and remove some of the topological quantifiers that go into it, you can take a true statement and turn it into a false statement just by swapping one of those things. Okay, so this is important that you understand what's going on here. Okay, and so here's kind of a list of topological notions. Okay, so topological notions in the complex plane. Okay, so we have a few terms to define here. So one is the notion of an interior point. So what is an interior point for a set? So Z0 is an interior point of a set S. Okay, this is a set of complex numbers. So Z0 is an interior point of set S that such that whenever there's a neighborhood of Z0, whenever there is a neighborhood of Z0 that contains only points of S. Basically, maybe I'll draw a picture here in a second. So Z0 is an interior point of a set S whenever there is a neighborhood of Z0 that contains only points of S. Before I draw a picture, I'm going to define a few more terms, and then I'm going to draw a picture that kind of takes care of all of them. Okay. So the notion of exterior point is when there exists a neighborhood containing no points of S. So Z0 is an exterior point of S if there exists a neighborhood of Z0 containing no points of S. Okay. Another type of point is a boundary point. So Z0 is a boundary point of S if it is neither an interior nor exterior point. Okay. All right. The set of all boundary points of S is called the boundary of S. Okay. A set does not have to contain its boundary. So let's go through all of these in one nice picture. So I'm going to draw. I don't even have to draw like a closed disk. I could even draw some region that didn't look like a disk at all, right? I could draw some like floppy region here. So in fact, maybe I'll do that. So here, I'm going to draw this region, right? So here is a region of the complex plane. Okay, so this region of the complex plane contains everything inside of that closed curve that I just drew. Let me get another color of pen somewhere. There we go. So I'll shade this a little bit. So here's my region. Okay. All right. And so Interior point, you might naturally say, well, that's a point like that. Why is this point an interior point? Well, just following the definition, there exists some neighborhood that contains only points of S. So if this region is my set S, then here's a neighborhood, right, around that point that only contains points in S. Now, notice that there are neighborhoods of this point that contain points that are not in S, right? If I made this big enough, I could have come all the way out here outside the set, and I would contain points from outside of S, from the exterior of S. But this is a statement about the existence of at least one set for which this works. Okay, and of course, you know, once you have one set, well, then any epsilon neighborhood where epsilon is taken to be smaller than the epsilon in that epsilon neighborhood is going to be contained in that neighborhood as well. So you get infinitely many sets for which this is true. And notice, even if you're very close to the edge here, that is still an interior point because I could come up with some extremely tiny epsilon neighborhood that is entirely contained in S, right? That contains only points in S. Okay. Similarly, right, a point like this is an exterior point because there exists this neighborhood about the point that doesn't contain any points of S. Okay. Again, I could blow up this neighborhood a little bit so that it actually intersected S somewhere, but being an exterior point means that there is at least one neighborhood that I can separate out from S like this. Okay, and if I have a point that is neither an interior or exterior point, what would such a point look like? Well, there. There's one. Notice that any neighborhood, no matter how large or small I draw that neighborhood centered at that point, that every single one of those is going to contain both points not in S and points in S. And there's no amount of shrinking that I can do here that's going to change that. Okay, so then this is what an interior point looks like. This is what an exterior point looks like. And this is what a boundary point looks like. Okay. All right. Let us consider the open disk of radius 1. So let's consider the open disk of radius 1. So here is open unit disk for radius 1. So this is centered at the origin. So here's the origin, 0. Here's distance 1 here, right? And it's an open disk. So what is the boundary of this set? If this is my set S, what is the boundary? What is the boundary of S? Sometimes you'll see notation that we use here. That's the del partial symbol, del S. This is boundary of S, so we'll use this notation sometimes. What's the boundary of this set? Well, the boundary is just that circle, right? That is the collection of boundary points. So the definition of the boundary of a set is the set of all the boundary points. So here's interior points. Maybe I'll use a different color so this doesn't look too stupid. So here's interior points, right, of my set. Here's what exterior points look like. And then the boundary points are exactly the points that would be here. Notice that S doesn't include these boundary points, right? This is a dashed line. So S doesn't include points that are located like here. But it's those points that no matter how big or small you draw the neighborhood, you're never going to be able to get rid of both points outside and inside. And the collection of all such points is this set, right? S is, right, this entire red region, not including the blue boundary circle, but the collection of boundary points is that blue circle I just drew. Now, this might seem really simple, and not worth much explanation. But I assure you that it can get really tricky dealing with a lot of these kind of concepts mathematically. It can be a little tricky actually keeping track of all of this stuff. And there's a lot of subtlety going on here that gets swept under the rug a lot of times. And so it's important to at least have kind of these basics down. So I wanted to come up with finally our definition of an open set here. So an open set, so I just gave you an example of this set S that didn't contain any boundary points, right? Its entire boundary was outside the set because this blue boundary circle was dashed, right? And so it turns out that we have a special name for a set like that, and that's the notion of an open set. So a set is open, okay, if it contains none of its boundary points. Okay. In fact, so it is a fact, okay, that a set S is open if and only if all of its points are interior points. This is kind of the key fact, okay? So just from this definition that it doesn't contain any of its boundary points, it basically means that the only candidate points that could be contained in S have to be interior points. So I'll let you reason that out just from our definitions that we've gone over, okay? But all of its points are interior points. Now, what this means, using the definition of interior points, is that around every single point in an open set, I have a neighborhood that contains nothing but points in that set. So basically, the main fact, I'll put a star next to this, is any point in an open set has an epsilon neighborhood centered at it, contained entirely in that set. Okay. This is the key property. Okay. What is important about this is that I have room to do stuff. Okay. To give you a simple analogy, remember what happened in calculus, right? Calculus of real functions. Whenever you wanted to deal with functions, say, that were defined on an open interval, right, versus a closed interval, questions about what happens at the endpoints for an open interval don't matter because the endpoints aren't included. So even over here, there's room to do stuff, and when I say stuff, I mean things like take limits from both sides. But here, right, at a point like this, there's no longer any room to do stuff. You can't take a limit approaching from here because none of these points are in the set, right? So you have to reformulate things and make sure that everything makes sense, doing only, like, I would say, a one-sided limit here, or doing things from one side for that function. That's one of the complications, and of course there are others. But the way to think about it is, in an open set, there is room to do stuff. Okay. So this is a nice characterization of an open set. Okay. There's also a notion of a closed set. You've heard of a closed set before, and in fact, a lot of the sets that you've dealt with before were closed, because closed sets have some nice properties as well. What is a closed set for us? So definition of a closed set. So a set S is closed if it contains all of its boundary points. Okay. All right. So there's some other definitions I want to define. So here's a definition of the interior. So the interior of a set S is the collection of all of its interior points. Okay. The closure, so the closure of a set S is the set containing all points of S and all boundary points of S. And here is a fact. The closure of any set is closed. So the closure of any set is closed. Here's another fact. A set is closed if and only if it is equal to its own closure. So if when you consider the closure of a set, it's actually just the set itself, then that means it already contains all of its boundary points, and so it's equal to the closed set. Okay, and so a set is closed if and only if it's equal to its own closure. Okay. Similarly, a set is open if and only if it's equal to its own interior. Okay. But I don't want to give you the false idea that a set must be open or closed. They're not really opposed in that way. There are sets that are neither open nor closed. There are sets that are both closed and open. So note, however, there are sets that are neither. So there are sets that are neither open nor closed. All right. So of course you could draw something stupid like here we go, right? Right, there's a set. Right, so it contains some of these boundary points, but not the rest, right? And all the points in the middle, right? So here's an example. Here's another example. It's actually simpler than this. Is what if I have a closed disk, but it's punctured in the middle? So a closed punctured disk. So if this is radius epsilon and this is happening at z0, this is actually just the punctured disk. Modulus of z minus z0 is less than or equal to epsilon. Right, so that is this punctured disk that includes the boundary and it includes all the interior points except that one. Right, except z0. Okay, so this is an example of a set that's neither open nor closed. You had very easy examples of this in the reals. Think of a half-open interval, right? Okay. So a couple more topological properties and then we'll be done. Notion of connectedness. Now here is where things already, there's a lot of subtlety going on under the hood here, but here things could get even trickier if we let them be, but we're not going to do that. We're going to take the easy way out here. So we have a definition of connected in a set. So a set S is connected if every point in the set can be joined by a polygonal line. If any two points, Z1 and Z2 in S, can be joined by a polygonal line consisting of finite segments. Okay. If you have taken topology, or if you know anything about it, you'll notice that this is not the same definition as usual for connectedness, because that definition is more complicated and way too general, and there's no need for it. So this is something that is, more equivalent to path connectedness. Okay, if you know a little bit about topology. Okay, and so for instance, here's an example, right? So let's say I have the closed set that maybe looks like this, right? This is connected because even if we pick points Z1 and Z2 like this, I could draw some polygonal line here connecting both of them that is entirely contained in S. Oh, I didn't include that. That's important. If they can be joined by a polygonal line entirely contained in S. Okay. Okay, so yeah, so connecting them like this is not allowed, because then two disconnected. Of course, if you took, for instance, if you took as your set S two disconnected regions, right? So maybe here's one and here's another, right? So your set S consists of two disconnected regions. Then if I take a point here and a point here, I cannot join these 2 points in a way that would consist of a polygonal line entirely contained in S. It would have to go outside of S, and that's no good. Okay, so that S is disconnected. Another example of a connected one is even like an open annulus, right? So something like the annulus, so such that modulus of Z is between 1 and 3. So this is an open annulus between circles of radius 1 and 3. So it's this region that doesn't include the dashed curves, right? So this is connected because I can pick a point here, and even if I pick a point that's on the opposite side here, I can still connect it easily with a polygonal line that lies entirely inside that region. Okay. All right. So, more terminology. A non-empty, this is just to save us words when we're stating these theorems later, because if you don't keep track of all this, if you don't do all this bookkeeping, the theorems would explode in length. That you would have to say like a paragraph of words, and it's just easier to tie up those paragraphs into single words here. So a non-empty open set that is connected. So non-empty just means it has some points in it. Open, you know what that means. Connected, you just saw what that means. So a non-empty open set that is connected is called a domain. Okay. So note that this basic neighborhood, right, any epsilon neighborhood, is non-empty if epsilon's positive, right? So it's non-empty, it's open, and it's connected. So it's a domain. So any epsilon neighborhood is a domain. So that's good. Okay. Few more properties. The notion of a bounded set. So a set S is bounded. Sometimes we will abbreviate this as BDD. just to save us a little bit because we're going to say bounded a lot. So a set S is bounded if every point in S lies inside some circle modulus of z is equal to some radius r. Okay. Another definition. A set S is unbounded if that's not true, if it's not bounded. That might be a pretty funny definition you can think of. What's the definition of being unbounded? Well, it's unbounded if it is not bounded. That's great. Okay, but that's good. That's exactly true, and that's perfectly fine. So what's the example of a bounded set? Well, even a set that's crazy like this, like the interior of a set like that, this is bounded because I can draw some big circle that all of these points are inside. What's an example of a region that's unbounded? Well, for instance, consider like the first quadrant, right? So like if I consider the first quadrant as my region, right? Then that's unbounded because, well, I can't, no matter how big I draw my circle centered wherever I like, that thing just goes on infinitely in that direction, so there's no bounding that region. Okay, couple more terms and then we're done with these. Okay, and so we have the notion of an accumulation point. So a point in S is an accumulation point if each deleted epsilon neighborhood of that point, so we'll call the point z naught, so every deleted neighborhood of z naught contains at least one point of S. This can be a tricky thing to visualize and actually figure out what it is that's going on here. But the important fact to note is if S is closed, then it contains all of its accumulation points. Okay. So, think about for a second what it would mean for a point to not be an accumulation point. It means that whenever there exists a deleted neighborhood of that point that doesn't contain at least point of the set, some point of the set, then that point itself is not an accumulation point. So to see an example, let's consider the set S that is defined to be the set of all complex numbers that are just I over n. Right, so it's the set of I over n such that n is just the natural numbers, so i.e. n is 1, 2, 3, and so on. So what does this set look like? This is a set of complex numbers that are, so the first one is here at I, right, and then I over 2, that's like here. And then the rest of them look like this. Okay, they're going down closer and closer to the origin here. Note the only accumulation point of this S is 0. That is here. Notice that this 0 is not actually contained in the set S. Right? But look at this thing that I drew, right? What do you think accumulation points are related to? So just looking at that, can anyone tell me what they think accumulation points might have something to do with? So I have a bunch of points and they're kind of bunching up, they're accumulating. But when you view it in this context, what does accumulating look like? What does it look like is happening? This is related to convergence. So questions of sequences converging, that's related to accumulation points. Okay, and so that's what's really being said here is this is just giving us terminology to deal with notions like convergence. Okay, so that is all of chapter 1 from the textbook taken care of. We're going to start on functions of a complex variable on Monday, and we'll be speeding through that stuff, getting to kind of like we want to be able to talk about analytic functions as quickly as possible here. Yeah, so Brian, yeah, is 0 considered a boundary point here? Well, this set S is actually a nasty kind of like disconnected set. It contains infinitely many points, of course, but it is a disconnected set here. It is not really a boundary point. Okay, I should be careful here. It is in the definition that we have used here. 0 actually is a boundary point. And 0 is a boundary point because any neighborhood of 0 here is necessarily going to contain some point of S, right? You can just keep increasing in here, right, to eventually be within any neighborhood you want. So yes, there's the way that we have defined these terms, you can think of 0 as a boundary point. Thinking of it as accumulation point is going to be better for these specific purposes because we're going to be able to tie that in immediately to sequences converging. You can do the same for boundary points. You just have to be careful what you're talking about. But yeah, yes, we can view it like that. And we'll talk more about those things when they come up in the next chapter. Okay, so I think that's it. I will see you all on Monday. So I was gonna have office hours today, but something came up and I have a bunch of appointments. So I'm gonna have to push what was gonna be this week's office hours to Monday. So Monday afternoon, and I don't want it to overlap with your tutoring hour. So Monday afternoon, starting at I think your tutoring hour ends at 1:45, so starting at like 2 p.m. I will host an office hours session where you all can ask questions, and that is doubly good because your homework is due later on Monday. So if you have any remaining questions about stuff, you can ask me then. So anyway, but I'll post an announcement about that on Monday. So anyway, I will see you all then. So have a good weekend.